Hello ELT132, this is Roger Young, and this video discusses the subject of excitation tables. So this is going to be used in the process of defining a synchronous counter. Then from defining the synchronous counter, you're going to generate a state table. Then from generating the state table, you're going to generate equations via Carnot maps, and then from these equations you're then going to generate the circuit. So the prior video you were given a circuit and you were asked to generate the state table, and then from the state table the state diagram. For now you're going to do it backwards. You're going to define what you want, generate a state diagram to the state table, all the way back to the circuit. One thing you need to understand in that process is the concept of an excitation table, and that depends on the flip-flop that you're using. So this particular video discusses the excitation for a JK flip-flop. So this concept is not very difficult to understand, but basically if you look at the transition over here, this is the Q output. This should have a Q written here, but they don't state it. But if your Q output is starting at 0, as they show here, and it ends at 0, basically there's no change. So what this means is that the flip-flop is in the reset state, right? Because the Q is 0. Or since it started at 0 and ended at 0, it's also in the no change state, right? So no change, JK can be defined as 0, 0, right? Or if you reset, if you're in the reset state, J and K would have been 0, 1. J would have been 0, K would have been 1. Then it would have been clocked, and then your output would be a 0. So in other words, if you look at these examples, K can be a 0 or K can be a 1. It really doesn't matter, because with this kind of transition taking place, you just need to make sure that J is 0. Alright? Now if you look at the next example, if Q is 0 and you want it to be a 1, well, you need to either toggle the flip-flop or you need to set it. Well, toggle, you know that when the toggle state, J and K are 1, 1. In the set state, J and K are 1, 0. So in this example, the J has to be a 1, if you notice, but K can be either 1 or 0. In either case, with this transition, if J and K are either one of these values and then it's clocked, then the flip-flop is clocked. When I say clocked, then the output is going to be in the set state. In other words, Q will be 1. And if you look at these, J must be 1, K can be either 0 or 1. Okay? Let's look at the next one. We're going from a 1 to a 0. Well, that's reset, isn't it? That's down here, right? Or it's a toggle. Got it? Because you're toggling the output from a 1 to a 0, or in reset, it's the same thing. You're setting Q low, right? So that would be a 0, 1. You know, if you look at this, it doesn't really matter what J is, does it? All that matters is that K is high. So hence you get a 1 for K. Remember, X means it can be either a 0 or a 1. It really doesn't matter, right? I think the book calls that I don't care state, right? The I don't care state. And finally, if you have a 1 to a 1, that's going to be either a no change, because it starts at 1 and ends at 1, or it's going to be a set, in which case the output ends at 1. Hence, for a no change, J and K need to be 0 and 0, or for a set, it needs to be J needs to be 1, K needs to be 0. When it's clocked, all right, your transition, it's going to be a 1. And this is what it means for your inputs. Obviously, J can be either a 0 or a 1. K is going to be a 0. So that's what these mean, right? And then further, what you're going to see is they aren't going to list this whole table like this. They're just going to show the transition and the J and K values. But this is where this condensed excitation table comes from, right? So if you look at the condensed excitation table, to go from 0 to 0, J has to be 0, K can be either 1 or 0. If your transition is from a 0 to a 1, J is 1, K can be either a 0 or a 1. If your Q output is 1 and you want to go to 0, then your J, it can be either a 1 or a 0, but K has to be 1. And if you want to go from a transition from a 1 to a 1, J can be either 0 or 1, but K must be 0. I hope this has helped you in your understanding of excitation tables. In the next video, we are going to use them to solve a problem. Thanks for watching.